In this video, we will go through the variation and the distribution of the samples. We will talk about how the sample means and sample variances differ in different samples of the same population. Knowing the variation, and the rule of it, is very important. It can help us correctly evaluate the estimation. Based on the samples drawn, it can also validate assertions about the whole population. Different samples return different means and variances. We call this variation of samples. For example, you have historical data of 100 days. You can compute the sample mean and the sample variance. Based on the statistics, can we find, or guess, the parameters? How close are the statistics to population parameters? By observing the data of 100 days, can we make a claim the numbers have a trend? All these rely on our understanding of sample mean distribution. As the samples are randomly drawn from a normal distribution, when you run to find the sample mean and variation several times, the results are different. Furthermore, the sample mean and variance are not changing arbitrarily. Instead, the changes follow some kind of rules provided that they come from the same population. Here, we take a sample, when sample size equal to 30, from a population with a normal distribution, mean equal to 10, and a standard deviation equal to 5. We will use some codes to generate the empirical distribution. The histogram of a sample variance is not normal, as you can see it is right-skewed, as you can see in the plot. We will also look into the sample means. We can see that the sample means distributes like a normal distribution. However, in fact, the variance of this distribution is smaller than the distribution of the population. Now, we will try to compare the two distributions. Mathematically, if we let the original distribution by having mean mu and variance sigma square, then this distribution of sample means will have the same mean mu, and a variance of sigma square over n, where n is the sample size. Let's try to plot them into the same graph. The red histogram is the population. We will also plot the distribution of sample means in blue. The two graphs are normalized to have a better view while comparing. We observe that the blue distribution has data more close to the center, which is mu. It indicates a smaller variance. Okay, what we have talked about so far is about a normally distributed population. What if the population is not normal? Let's talk about the central limit theorem. By the central limit theorem, if the sample size is large enough, the distribution of the sample mean will be approximately normal, and the distribution will be similar to the distribution of sample means we suggested previously, which has a mean mu, and variance sigma square over n, where n indicates the sample size. In fact, we can apply the theorem to all distributions in general, while considering the distribution of their sample means. Let's look at these codes. We have made up a random distribution, for example, -100, +100, 0, etc., as you can see. We try to use different sample sizes and plot different histograms. We can see that, when the sample size is larger, the histogram looks more similar to a normal distribution. In this example, we use 2 and 1000 as the sample sizes respectively. We can observe that the histogram with sample size equal to 1000 looks more similar to a normal distribution, like a bell shape. Great! In this video, we mainly talked about the distribution of sample means, and described the probability rule of variation of sample means. It will be used in the next two videos to explore two important quantitative statistical tools: confidence interval, and hypothesis testing. See you in the next videos.